Hey everyone, welcome to math class today on Monday, April 20th. After a crazy weekend of weather, waking up with Saturday morning with like 5-6 inches of snow on the ground, and then yesterday was a beautiful day, and then Monday now, math class. Try to get you thinking a little bit about surface area on problems 1 and 2 here for the entrance task. I'll even give you, if you want, save you the step of going back to look at your notes for the formula. For this one, you should be using the formula that the surface area is equal to 2 pi r squared plus 2 pi r h. Alright, so go ahead and take a second to find those to get back into the swing of things from last week. Okay, after you're done pausing the video, I'll go over the answers here. Hopefully you tried it. These couple of questions. So for number 1, we've talked about just finding the area by finding the area of each face and then adding up all 6 areas because there's 6 faces on this rectangular prism. So the top and the bottom are each 42 because 7 times 6 is 42. The left and the right are both areas of 30 because 6 times 5 is 30, and the front and the back are both 35 because 7 times 5 is 35. Add up all of those and you should get 214 centimeters square. That's the surface area. So it's the area of all the outsides of that cube. For the cylinder here, use the formula 2 pi r squared plus 2 pi r h. Everywhere you see an r, plug in a 5. Everywhere you see an h, plug in 16. And remember that we've defined height as the distance between the bases. So even though the cylinder is laying on its side, we've called the three-dimensional height the distance between the bases, and distance between the two circles in this case. Alright, and then do the order of operations. We do the exponent, 5 squared is 25. Make sure we do all multiplying and dividing before we do the addition step. We'll do the addition step last. We get 210 pi centimeters squared. That's your answer in terms of pi. If it did say nearest tenth or nearest hundredth, you would just plug that into your calculator, 210 times pi, and round appropriately. Alright, so hopefully that's a little bit of a quick review from what we did last week and on that little practice quiz. Today we're going to be shifting gears and looking at volume. Okay, so now it's going to be three-dimensional space. Now, by the way, if you haven't done so already, I posted a video of a different guy teaching, not because he's necessarily a better teacher, maybe he is, you can decide, but he had really good graphics to accompany the three-dimensional stuff. So without me being there in person to show you shapes you can actually put your hands on for these, that video that I posted on Friday's lesson, I would still recommend to go back and watch it if you haven't, because it kind of puts this all together of being able to kind of really see the difference between surface area and volume. Alright, so please go to your notes on page 14 if you haven't already. So volume is going to be how much three-dimensional space does an object have. So how much space does it take up? But compared to surface area before was just the area of the outsides all added up. So basically, like, how much paper would it take to wrap a 3D object with surface area? Volume is how much space something takes up. So again, if you imagine, here's like a book I have right now to try to have a little bit of a something to show you here. If you had to tell me what shape this book is, hopefully you would tell me that it's a rectangular prism, right? It's pretty much solid, especially if we wrap this in paper, it would seem pretty solid here, and it has, 3 dimensions to it. It has the distance this way is one dimension, the distance this way across, which is another dimension, there's the second dimension, and then the third dimension is the thickness of it, how thick it is from cover to cover. Okay, so this is a three-dimensional object, a rectangular prism. But the way we can think of it, and the reason I chose a book for it, is because we think of a piece of paper as kind of having, is kind of being like two-dimensional area. a piece of paper actually does have thickness. It's just so thin when we have a piece of paper that you don't typically think of a piece of paper as like a rectangular prism because the thickness is so thin, right? Trying to that doesn't even pick up on the camera, right? All right. So the idea of volume is that one way you could find volume is if I took the area of the front cover of this book, okay? If I took the area of the front cover of this book, that would be pretty much the area of that front cover piece of paper. However, if I could stack all of those papers together, those papers add up to have a thickness, so that basically if I take the area of, let's say, the back cover, this bottom cover piece of paper here, if I took the area of just this rectangle and then I multiplied it by the entire height of this book, when I lay it down like that, the thickness of this book, well, that two-dimensional area will stack up, stack up, stack up, stack up, stack up, stack up, continue to stack up as you go through all the pages until you get the entire thickness of the book. Okay, so the good news is, if what I'm trying to explain to you doesn't make any sense, this idea of I could take the area of one of the pieces of paper and then stack it up, those pieces of paper, until I get the whole thickness of my book, it doesn't have to, because there's formulas for it. The only thing this really helps us is to understand where these formulas come from, is that you're basically taking the area of a base and then, for prisms, stacking it up the entire thickness until you get the opposite base that's across from it. And you can see there's a cover on the front and a cover on the back. And if I can just stack those pieces of paper, the whole thickness between those covers, I'll have the entire amount of space that this book takes up. Because this book definitely does take up space when it's that thick. Mental game of baseball. I don't think I actually ever got through that whole book, but I remember when I got it. But it was a good paperback that I found for this lesson. So let's take a look at the formulas and examples. You have these written down here. We'll come back to the pyramid example in a second. We'll look at these two prisms here first. So if you have a rectangular prism, it turns out that you can just do length times width times height. Just multiply, it's as easy as it goes. Multiply the three different dimensions and boom, that's it. And that's what most people think of with volume. Oh, it's just length times width times height. Well, that's for any rectangular prism, it's that easy. All right. If you look down at the third example here, a triangular prism, okay, it's not quite as easy. It's this capital B times H is the area of the base, which, since this is a triangular prism, the base would be the triangle, the area of the triangle, times the height of the prism, which would be the distance between the bases. So it can get a little bit confusing because I have two H's in two different formulas. I have this first mini problem that I have in this problem. This is a 2D problem, two-dimensional problem that's only talking about the area of that front triangle. So when I basically cover up everything else in this problem except for that front triangle, I would say when I do this mini problem first, the base of that triangle, small b, is 3, and the height of the triangle, again, when I'm only concentrating on this front triangle, the height of the triangle is 4. That allows me to say that the area of that triangle, my base here, is 6. But then when I use the formula for volume, the area of the base times the h, now the height of the prism, because this is now talking about the three-dimensional volume, that the height, the distance between the two bases is 6. So I put that value of 6 right in there for height. The other video I posted, they called this the other length, like the length between the bases or the distance between the bases. However you want to think of it, but if you can understand the concept that it's the area of the base as you stack up those papers. If you imagine I had a triangle piece of paper here and I just stacked up that triangle piece of paper all the way till it got to this other base, that would now, all those pieces of paper together would take up this exact area, which is what I'm trying to do for volume. Notice that the units now are cubic units, so I got centimeters cubed for these two. All right, and then it turns out, all right, for a pyramid, the pyramid is the same formula. It's just divided by 3. It's basically like the pyramid when they, instead of having another base, it goes to a point. It basically takes the volume and cuts it, by a third, okay, into a third of what it would be if it was a pyramid. So in other words, if I had a rectangular prism that was 9 by 9 by 5, the rectangular prism would be 9 times 9 times 5. However, when I have a 9 by 9 by 5 pyramid, the volume of it would be 9 times 9 times 5 divided by 3. I have to divide by 3 at the end. So it's like the same formula, but divided by 3. Okay, so there's your volume for this pyramid, 9 times 9 times 5 divided by 3. So that's the volume of a pyramid. So prism is just, if it's a rectangular prism, length times width times height. If it's any other prism, it's the area of the base times the height, and that's the three-dimensional height. The height is the distance between the bases, right? And if you have a pyramid, it's your length times width times height, the volume of the prism, divided by 3, and it makes it, instead of the volume of the prism, it makes it the volume of the pyramid. Again, it's harder. This is a little bit of a harder lesson to teach online, I think. So watching the video from Friday, if this is confusing for you, should give you better visuals. The video of that other guy that I taught should give you better visuals to understand this. If you look at the formulas and don't overthink it, that's also helpful, as long as you understand where these formulas come from, right? That you understand what the letters mean in these formulas. And these ones will be your favorite ones. These will be the ones that make you happy, because those ones really are pretty easy. Okay? So after you're done watching this lesson, I'll give you just the happy problems to try for tonight. So why don't you just do page 15, which is all volumes of rectangular prisms, like example 1. So it should be an easy one to start, and then we'll build off of that for tomorrow. Okay, so page 15 for homework to try. I hope you guys have a good Monday, and we'll talk with you tomorrow. Bye.